I've been going over your work on partitions. So now you've begun to embrace some proper rigor. I think you should meet Major McMahon. He's the leader in combinatorics at the university and also happens to be one of your most vocal opponents. He says partitions can't be done, especially by the likes of you.
Then you better start counting very high.
Enter at your own risk. You fail on primes and you think you can just turn round and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
No, I will. By hand. By slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can do it.
Well, here we are, P of 200, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
Sometimes in math, an equation can seem so simple. You know, like the equation force equals mass times acceleration. But some formulas, well, they seem to come from another planet. And one that comes to mind is this. The Hardy-Ramanujan Asymptotic Approximation formula for the partition counting function. Alright, now, how many different ways can you write the number 15 as a sum of positive integers? How long would it take you to calculate it? Could you even estimate how big this number is? And did you guess 176 to be the answer? Were you even close? P of 15 is equal to 176. But the more important question is, was this predictable or just computable? number of ways you can partition 15 is 176 different ways. But how would you find a formula that can predict these values without having to generate all of the values? Exploiting the power of modular transformations and the calculus of complex variables, G.H. Hardy and Srinivasa Ramanujan would develop a method known as the circle method. Let's encode the problem. Okay, so the first thing we're going to do is begin with the Euler product function, E of Q. Now, taking the reciprocal of E of Q, one might recall that this yields the partition counting function generating function, a power series whose coefficients are the partition counting function. Now, our goal is to extract that coefficient P of n without having to evaluate the entire series. And the way that we're going to do this is via complex contour integration, that is, exploiting the power of complex exponentials. You could call Augustin Louis Cauchy the father of complex calculus. Let f be a holomorphic function on an open set containing a region D and its boundary C. Then for any closed contour C containing D, we have a closed contour integral that equals 0. Geometrically, if you have a closed contour and the function is analytic within that region, then the contributions will add up to 0. They will not contribute anything. And this is known as Cauchy's integral theorem. And it leads to the cornerstone of complex function calculus, which is known as Cauchy's integral formula. So analytic functions have no circulation. They do not accumulate anything when you go around the loop. So Cauchy's integral formula says that if f is analytic inside and on the closed contour C, and a is a value inside of the contour C, then f of a can be evaluated using this closed contour integral formula. You can compute the value of a function at any point by integrating around it. And this formula also allows us to define derivatives for a function, a complex function. Coefficient extraction. Suppose we have a function of a complex variable given as a power series, and let's say that we want to extract the nth coefficient. Cauchy's formula allows us to do just that. And expanding the integrand and integrating term by term, we can get a piecewise integral that kills off all other values in a series except for the one that we want. So here, expanding out this series and integrating term by term, we get the piecewise integral which only evaluates to 2 pi I when k is equal to -1 and 0 otherwise. The only term that survives is the one where m minus n minus 1 is equal to negative 1, thus m is equal to n. And so Cauchy's integral formula gives us a way of extracting the coefficient that we're interested in. The contour integral acts like a perfect filter if it isolates exactly one coefficient. Partitions meet complex contour integration. Let capital P of Q be our partition generating function, and then our integrand P of Q over Q to the n plus 1 is given by this series. Integrating around the circle center at the origin, our contour integral reduces down to an integral of this form. So, an integral of the form q to the k dq is going to be addressed first by parametrizing the circle, letting q equal r e to the I theta. And so theta ranges from 0 to 2 pi, and thus we can define q to the k power and dq as well. So in polar form, our integral takes on this form as a function of theta, and of course simplifying this integral, we get the following relation. Now if k is not equal to negative 1, this integral, it equals 0. However, if k equals negative 1, that's where the interesting stuff happens. This integral is equal to 2 pi I. And so, we get a piecewise integral who kills all other values except for the one that we want. So now we've established how to extract P of n by evaluating this contour integral. And substituting in the product form for P of Q, where r ranges between 0 and 1, it's this contour integral that we need to evaluate. Next, we're going to reparametrize the circle, and we're going to do so on the interval from 0 to 1. So, with a little calculus and a little finesse, we get our integral to be of this form. And it simplifies once we do a little rearranging of terms to look as follows. Introducing the product form of our p function, the complete integral looks like this, and thus we have the normalized partition function on the interval from 0 to 1. Our mission is to get an asymptotic approximation for P of n, which means we will have to investigate what happens as n approaches infinity. Asymptotic growth is about how a function behaves as the input gets very large. Consider the two functions, f of n equals n and g of n equals n squared, one linear, one quadratic. At first glance, on a smaller interval, they don't seem to behave all that differently. They grow rather in the same fashion. The gap between them isn't that great. However, for asymptotic growth, we have to zoom out and view at a larger scale, so we can see what the large-scale asymptotic behavior is of these two functions. And as we look at what happens as we let the scales go larger, we see that the gap between these two functions becomes enormous. The gap between their values increases rapidly, so n squared eventually dominates as that gap becomes enormous, and asymptotic growth compares functions based on their eventual or end behavior. Now, singular points or singularities are points about where functions break. And with complex functions, these asymptotes are referred to as poles or spikes. So asymptotic growth is really about its global behavior around a specific point that might spike, adding contributions to a contour integral. Alright, now recall that the product form of our generating function looks like this. This is a perfectly nice function inside the unit disk where q is less than 1. But at q equals 1, this function blows up. A singularity occurs. So for partitions, q equals 1 is the dominant singularity, giving the most contribution to that integral. Now to recover P of n, using the Cauchy integral formula, we look at as n goes to infinity that the integral is dominated where P of q is largest, near the singularities. And so the closer the contour is to that, the greater the contribution. Asymptotic growth comes from the behavior that is close to or really near q equals 1. Now, dividing the interval between 0 and 1 means that we need to organize the fractions within that interval properly. And to do this rigorously, one must employ fairy sequences. A fairy sequence of order n is the list of all fractions in simplest form between 0 and 1 in value order. The denominators are bound by n, and no overlaps occur in this arranged order. So for example, a fairy sequence of order 5 gives this list of fractions. These fractions all have the key property that neighboring fractions have a special relationship. If a over b and c over d are neighboring fractions, bc minus ad equals 1, and we can create the mediant that sits between these fractions as a plus c over b plus d. Thus, fairy sequences organize the unit circle by breaking it into arcs centered at rational points. Fairy sequences are the best rational approximations to real numbers. So if we consider evaluating our partition function integral by cutting the unit circle into pieces centered around rational points where theta is approximately h over k, with two neighboring fractions we can then define boundaries between these, in other words, no overlaps. The arc for a fraction is then given over a certain interval that doesn't overlap, covers the entire circle, and gets smaller as n goes to infinity. The simpler the fraction, the more space it gets on the unit circle. So now we'll focus in on the points of interest. Starting from our normalized integral on the interval from 0 to 1, we will focus our attention on the major arc neighborhoods. Suppose theta is near a value h over k where the greatest common divisor of h and k is 1. Then for small values of phi, we can write theta as hk plus phi, and call this the local coordinate near the rational point. Then we can rewrite our q coordinate as follows, where we can get the exponential to split into two pieces. So near the rational point, q is near a root of unity, being pulled slightly inward by a factor of r, and then slightly rotated by a small phase factor, e to the 2 pi I phi. Now if we substitute this into our integrand, we get this expression, again splitting the integrand exponential into two parts, one with a constant root of unity phase and one with a local oscillation phase. Thus, locally the integrand becomes this expression. So taking a contour integral around a small arc around h over k, this local integral can be called its first local form. Now this allows us to analyze one slice at a time and not the whole pie. We isolate the contribution, and it allows us to ask the question, how does P of Q behave near the roots of unity, and how large are these contributions from this particular arc? Going one step further, P of Q has its product form, its local product form, in this form. So this allows us to see where the special local behavior comes from. Why do the roots of unity matter anyway? The dangerous factors are those for which e raised to the 2 pi I m h over k equals 1. Since the greatest common divisor of h and k equals 1, this happens exactly when m is a multiple of k. Thus we can write m as L times k, with L being an integer, and then we can reduce the exponential to equal e to the 2 pi I LH equal to 1. This means for the terms such as the ones shown here, our local terms, the value becomes very small when r is close to 1 and phi is very small. Therefore, in our analysis, the value of the product spikes near roots of unity. Now, since the idea is that the dominant contribution of the integral comes from the part of the contour where q is very close to 1, moving near q equals 1, we write q equal to e raised to the negative t, where t is greater than 0 and t is small. So as t approaches 0, e to the negative t approaches 1. Thus, the natural way to study the generating function is near its dominant singularity. Letting q equal e raised to the negative t, we get the product to be this product, and it grows extremely fast as t approaches 0. So its leading behavior is p of e to the negative t is approximately pi squared over 6t. But why is that? Where does that come from? Well, if we let L of t equal the log of p of e to the negative t, that allows us to turn the product into a sum, and then ask the question, how big is L of t when t is tiny? If we expand the logarithm as a power series, that allows us to write L of t as a double sum. So the expanded logarithm, given as this power series, included in L of t, where x is equal to e to the negative mt, we get the following expression, one with which we are free to swap the order of our summations. And of course, by doing this, this yields a geometric series in powers of m. And that allows us the advantage of the convergent value of that geometric series, given here. And of course, simplifying that expression reveals a sum which you may recognize as having Euler's fingerprint on it. That is, if we take L of t to be this summation, when t is small, r of t is also small for many values of r, and therefore for u, e to the u minus 1 is approximately u, so heuristically, this becomes 1 over r squared t. By substitution into the sum, the summation of 1 over r squared t is pi squared over 6t, which is exactly where Euler's fingerprint, aka the Basel problem, comes in. So if L of t is approximately pi squared over 6t, we get p of e to the negative t approximately equal to the exponential of pi squared over 6t, which is the source of the dominant exponential behavior. The integrand also contains a value of q to the negative n plus 1. So this is equivalent to e to the n plus 1 times t. Therefore, the expression e to the negative n plus 1 is equivalently e to the nt, the second exponential contribution to our integrand. Thus, p of q over q to the n plus 1 is approximately equal to the exponential of pi squared over 6t plus nt. Now, to simplify our expression, our exponential integrand, let 5t equal pi squared over 6t plus nt. The dominant contribution should come from the value of t where 5t is optimally balanced. If we want to find that balancing point, we set the first derivative equal to 0 and solve for t. The first derivative being given here set equal to 0, and solving for t, we'll call that t naught, is equal to pi over the square root of 6n. So by substituting this back into the function phi, we get the following value: pi multiplied by the square root of 2n over 3. And so p of n is approximately equal to some prefactor times this exponential. And thus we have some, what we'll call an amplitude function, a of t, or a prefactor, that we want to determine. So let us determine the prefactor of a of t. And to do this, we will employ a modular transformation via something called the Dedekind eta function. The Dedekind eta function is given in its product form here. By choosing tau equal to it over 2 pi, the exponential takes on the form e raised to the negative t as desired. And this product is now expressible via the eta function evaluated at a tau function, which now we just have to focus our attention on what is the value of that eta function at that particular tau value. So now we need to know what eta of I of t over 2 pi is when t is very small, and we're going to use the modular transformation of the eta function under inversion, which given by this formula, can be equivalently written in this way. So tau equal to it over 2 pi gives negative I tau equal to t over 2 pi, and so we may write eta of it over 2 pi in this fashion. Inverting this then gives us this. So now all we have to do is understand eta of 2 pi I over t. Taking out the eta function in its product form under the substitution, we get eta of 2 pi I over t to be equal to this, with a prefactor which shouldn't feel as surprising as it does. So eta of 2 pi I over t is approximately e to the negative pi squared over 6t, which means its inversion is approximately e to the pi squared over 6t. And thus p of e to the negative t is equal to this, and as e to the negative t over 24 approaches 1, the dominant asymptotic behavior is as follows. Thus we can conclude that this means that the amplitude function a of t is equal to the square root of t over 2 pi. Next, if we want to understand the integral geometrically, it becomes clear that we are dealing with a narrowly peaked or spiked curve which resembles a bell curve, a Gaussian distribution. The exponential dominates everything. The integral is essentially determined where phi of t is greatest. So the full integral represents something where the contribution mostly comes from a spike near T0. Focusing in on a small neighborhood of T0 allows us to look at this thing as a Gaussian distribution. Well approximated by a Gaussian allows us to evaluate the integral, and thus to find the point T0 where the peak occurs, we find where phi of T prime is equal to 0. And so since the peak is a maximum, the second derivative of phi is negative concave down, and the Gaussian kernel reveals the quadratic nature of phi of t. Thus, near the peak, we essentially freeze the amplitude and analyze the quadratic structure near the maximum. So our exponential function, e raised to the phi of t, is approximated with this quadratic approximation, a Gaussian. If we freeze the slow part, that is the amplitude, that means we want to approximate the amplitude at the peak of this Gaussian distribution. This will allow us to extract constants out of our integral. Recall that a Gaussian integral is of this form. So our integral gives this as a result. And so we have our width, our Gaussian width, to be given by this equation. And once we evaluate everything at the peak T0, we will be able to get an approximation for the integral. So if the idea is to look at our integral as the area under a Gaussian curve, that area is essentially its height times its width, where the height is given by a of t e raised to the phi of t evaluated at the peak T0. And the width of the Gaussian mountain comes from the evaluation of the Gaussian integral via the standard methods. Now let's evaluate some of the constants. Recall that our T0 value is pi over the square root of 6n. Evaluating phi at T0 gives us the value of pi square root of 2n over 3. So e raised to the phi of T0 is e raised to the pi square root of 2n over 3. The second derivative evaluated at T0 is 6n raised to the 3/2 power over 3 pi. And our amplitude function, a of t, evaluated at the saddle point, is the square root of T0 over 2 pi, which is the square root of 1 over 2 square root of 6n. So if our integral is approximated by these constants and this integral, and we apply the Gaussian identity, we get this for our integral. Now there's also a factor of 1 over 2 pi I in front of our contour integral. And we only care about the magnitude or size of this factor, which is 1 over 2 pi. So multiplying all of our factors together, we get an evaluation that simplifies to 1 over the square root of 2 pi phi double prime evaluated at our saddle point. And thus our approximation for P of n is all dependent at the evaluation of all these constants at our saddle point. So our width function evaluates to this, and multiplying all of this together, we get the prefactor of 1 over 4n square root of 3. So our final result is that P of n, in its asymptotic approximation, is 1 over 4n square root of 3 multiplied by the exponential of pi square root of 2n over 3, the Hardy-Ramanujan Asymptotic Approximation formula for the partition counting function. So here it is in its summary. We started with a partition function, a partition generating function, and the goal was to extract the coefficient of that using the Cauchy coefficient formula. Once we evaluated that and established that, we used the transformation of modular transformations of the generating function via the Dedekind eta function to evaluate some of the prefactor constants that we needed for our asymptotic approximation. Setting this up as a Laplace integral and evaluating at the saddle point, which really boils down to evaluating a Gaussian at the saddle point, we were able to extract some of the coefficients needed for our asymptotic approximation. And again, using the Laplace saddle point method, the normalization from the Cauchy integral, the amplitude at the saddle, and the Gaussian width at the peak all allowed us to evaluate and assemble the final results to get the Hardy-Ramanujan asymptotic formula for the partition function. And this approximation gets better and better as n gets larger. The exponential e raised to the pi square root of 2n over 3 gives the explosive growth, where the prefactor of 1 over 4n radical 3 comes from the geometry, height and width, of the peak. And in summary, we have the whole process of the Hardy-Ramanujan approximation for P of n from start to finish. And with that, I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.